This episode of Real Engineering is brought to you by the Royal Air Force and the Briggs Automotive Company, who are currently holding an engineering design competition for young engineers. One of the moments that will always stand out in my life is watching the joy and excitement of the engineers at JPL celebrating the monumental task they had just completed. They had just landed a 900-kilogram rover the size of a Mini Cooper on another planet. The Mars rover is bursting at the seams with engineering innovation. I could detail the insane landing process and any of the multitude of engineering marvels on board, but today I want to discuss something you may not have put much thought into, something we use every day on Earth: tires. The wheels of the Mars rover have been one of the biggest technical difficulties encountered on the mission, accruing substantial damage through the rough Martian terrain. Surely the engineers at NASA could have predicted this and designed something better. Well, not everything is as simple as it may seem. Even on flat, hard ground, the rover has a top speed of 0.15 kilometers per hour. Yet this snail's pace still has enough force to tear holes into the aluminium wheels of the rover. The engineers have some strict criteria that made the job more difficult. The wheels need to be stiff enough to support the weight of the rover. At nearly 1 ton, that isn't an easy task. The wheels need to be as light as possible to reduce launch costs, and must be able to maintain traction and navigate the unpredictable Martian terrain. The current record holder for the longest journey on an extraterrestrial body is held by the Opportunity rover at 45 kilometers, with the previous record being held by the Russian Lunokhod 2, a lunar rover. Curiosity has racked up just 20 kilometers to date. All Mars rovers have used solid aluminium wheels. The Sojourner, Opportunity, and Spirit rovers all used the design successfully, but the Curiosity rover is much heavier. Each wheel on the Curiosity rover is about half a meter in diameter and 400 millimeters wide, milled from a solid block of aluminium in a similar fashion to the methods described in my Bloodhound SSC video. But unlike the Bloodhound, the Mars rover wheels are milled to just 0.75 millimeters thick over the majority of its circumference. Damage here isn't all that surprising. 0.75 millimeters thick is the same thickness as a credit card. Running a nearly 1 ton vehicle over a sharp rock would be expected to damage aluminium that thick. NASA simply underestimated the roughness of the terrain. More worryingly though, the load-bearing threads, which are about 6.4 millimeters thick, are also damaged, and if they continue to break, the wheels will become useless. The Mars rover cost $2.5 billion to develop, and it employs a nuclear reactor for power. Extending the life of this project was top priority for its engineers, and so finding a solution to this problem has been fairly high on NASA's list for future projects. So what other designs could we use? To reduce the chances of the wheels experiencing a stress that could damage them, we want them to be able to bend and conform to the terrain. This is what our rubber air-filled tires do on Earth. Land Rovers drive over similar rough terrain without any major problem. So why not use tires like this on Mars? Temperatures on Mars can dip as low as minus 130 degrees Celsius. Temperatures this low would transform rubber from an elastic material, capable of absorbing stress, to a brittle glass-like material, making it useless for this application. Rubber would also degrade from the UV radiation it would be exposed to on the surface of Mars. On top of this, weight savings is also top priority, and rubber wheels with thick rubber, steel reinforcement and a rim are actually quite heavy. The lunar rover used flexible steel mesh wheels with a stiffer inner frame to prevent over-deflection and thin strips of metal attached to prevent the wheel from sinking into the lunar soil. This option was studied for applications on Mars, but the lunar rover had a mass of just 450 kilograms compared to the 900 kilograms of the Curiosity rover. Combine this with the higher gravity on Mars and it made the wheel unsuitable for the application. The wheels would simply not be able to hold the weight of the vehicle without deforming permanently. But Goodyear, who developed the original lunar wheel, has been working alongside NASA, and in 2010 they were given the R&D 100 award for this spring tire, which could be the solution to our problems. Being both light, capable of bending and conforming to the terrain without permanently deforming, and capable of holding the weight of the heavier rover. So what's its secret? What makes this spring tire different to the ones on the lunar rover? They use a new age material that has some incredible properties, not just for applications in space, but right here on Earth. This spring tire uses a material called nitinol. Nitinol is a nickel titanium alloy that has been named a shape memory alloy, and for good reason. You can bend and deform it and then just apply a little bit of heat and it magically returns to its original shape. It remembers its original shape. That is incredible, but nothing is magic in this world and everything has an explanation. Here is how it works. Typically, when a material is stressed, one of two things can happen. If the stress is below its yield point, the material will deform elastically like a rubber band and return to its original shape when the stress is released. Alternatively, if the material is stressed beyond its yield point, the material will deform permanently, and when the stress is released, the material will not return to its original shape. So how does this permanent deformation occur? If the bonds are not broken, the material should return to its original preferred crystal lattice orientation, but when sufficient force is applied, small defects in the crystal lattice are able to move. This is what is happening to the wheels of the Mars rover. When driving over pointed rocks and gravel, the stress exceeds the yield stress, and thus the wheels are gradually picking up permanent deformation, and eventually cracks will form and the material will fracture. Deformation occurs slightly differently for nitinol, as it has some unique properties due to the internal crystal structure. When nitinol is below a certain temperature, it has a crystal structure called martensite. Its crystal structure is arranged in such a way that it can accommodate deformation very easily. Martensitic nitinol forms grains of twinned atoms where the direction aligns. When stress is applied, these twin grains deform and align to best absorb the stress. Particular twin grains can grow at the expense of others. This is called detwinning. This, like the dislocation movement in other metals, is permanent without external energy providing the energy needed to revert backwards, but nitinol can get that energy from heat. Upon heating, the nitinol forms austenite, an ordered, regular crystal structure, which effectively resets the crystal structure, and when the nitinol cools again, the nitinol remembers its original shape. What makes nitinol even more amazing and useful is that this transformation temperature can be tailored for different applications. In general, increasing the titanium content of the metal will increase the transformation temperature. This is an incredibly useful property, and it has found many applications across many industries. Let's say we want the metal to remember its shape at 37 degrees Celsius, body temperature. Can you think of any applications where this would be useful? I'll give you one. Traditionally, when stents, which are tiny tubes used to clear blockages in arteries, are being deployed, a small balloon is used to inflate it and plastically deform the stent into shape. However, this often places force on the lining of the blood vessel, which can damage it and cause it to form scar tissue. Many stent designs now employ nitinol, which has been tailored to remember its shape at 37 degrees Celsius, and so when unsheatheded, it automatically expands into place without placing excessive force on the blood vessel. So how is this useful for the Mars rover? Do we have to apply heat to the metal so it can recover its shape after running over a particularly big rock? No. Luckily, nitinol can be induced into that martensite to austenite transformation through stress and strain. And so when the stress passes a threshold, it actually causes the crystal lattice to transform to austenite. And when the stress is released, it returns to martensite and the metal recovers its shape. This is called superelasticity, and it is the property that allows these new Mars rover wheels to deform right down to the rim and still recover its shape after. This, combined with the interlocking coil design, allows the tyre to tolerate strains in a way no other tyre could, while surviving the harsh Martian environment. These tyres could appear in NASA's designs for future Mars rovers, like those planned for launch in 2020. It's easy to think something as simple as a wheel will never be reinvented, but there are always ideas and opportunities for people willing to put the work into thinking about them. That's why I've teamed up with the Royal Air Force and the Briggs Automotive Company to bring you an exciting design competition for young engineers. We want you to brainstorm designs for a new Mars transport vehicle that improves on previous designs in some way. We want your most innovative and creative ideas. Think from the ground up. What problems will the Mars rover encounter? Have you ever thought about how we communicate with a vehicle on another planet? The top prize winner will have their idea developed and made into a 3D model by the Briggs Automotive Company. They'll also win work experience at the pioneering BAC factory in Liverpool that produces the world's only road-legal single-seater supercar. For more information, head over to the Starship YouTube channel. A link for that is on screen now. As always, thanks for watching, and thank you to all my Patreon supporters. If you would like to see more from me, the links to my Instagram, Twitter, subreddit and Discord server are below.